Swayam Prabha, Digital India, Educated India.
So this is the slide in which we had a pretty animated discussion also towards the end, and this is where we ended. So the take-home message is that we now understand quite a few things in somewhat greater detail. All of you knew about essentially first law of thermodynamics, or the conservation of energy. There's nothing great about that. We now know essentially two stuff. Additionally, we have gained additional knowledge, I would say. One of them is a very important thing for many engineering processes, is what is how to handle the first law, or the conservation of energy, right, for a flowing system, or for a continuous system. Not exactly flowing system, it's continuous system. Or in other words, in the previous class we talked about the rate form of the first law, or the conservation of energy. And then what we have also understood is so first thing we understood is this. And of course, the signs are there. I mean, don't worry about the signs. Depending on the process, the sign will change. Or this all of us understand now clearly. Then the other stuff we understand is the components of energy, which is the kinetic energy plus the potential energy plus the internal energy, right? And then we understand for a system like ours, which is going to be in most cases static, right? It can either have a fixed boundary or a rigid boundary. In fact, fixed boundary is certainly not completely out of place, because in many cases, for example, whenever you have solved this thermodynamics problem, you have so far, to be very honest, had a mechanical engineering perspective of that. So most of the time you were bothered about the pressure volume type expansion and the work done and stuff like that. Of course, those are very, very important in many settings, and you have done the thing correctly, right? So therefore, most of the time, whenever we talk about energy balance and stuff like that, the examples that come to your mind are like a frictionless piston and all these things. And now this class also understands why the word frictionless is so very important, so that you can use the energy conversion equation, right, without worrying about the dissipation factor, which is essentially interconversion of work into heat, right? But what we understand is that for the type of system we are going to look into, reactors, storage vessel, fluid flow, and stuff like that, it's going to be fixed somewhere, right? You do not roam around with a reactor, nor you are going to run away from here to a hill station or something like that. Or it's very unlikely that you have a system that is on a high-speed moving train and things like that. And therefore, most of the problems, realistic problems that we will be solving, is that not this, but when you talk about the change in the energy between state 1 and state 2, the change in the kinetic energy and potential energy in most cases is going to be 0. And therefore, what remains is change in the internal energy. So in many cases, this equation will get replaced like this, which we now understand well. And also we now understand about the different components of internal energy. So we have internal kinetic energy. The most important realization is this is a function of temperature. We have internal potential energy, which is not a function of temperature. And then we have associated internal energies due to vibration, rotation, etc. Now, this is the concept we have. So in most cases, the type of system that you are going to handle, right, it's sort of you are going to supply some heat, right? Or what can also happen is you have a system, let's say we are not going to talk right now about this. You have two reactants which react and it forms two products, right? And then, so this is essentially a chemical reaction. And we also know that chemical reactions, apart from just writing something plus something leading to something, C plus half O2 equal to C plus O2 equal to CO2, we also know, all of you know, that reactions can be associated with thermal effects. That's why you have this concept of exothermic reaction and endothermic reactions. And I'm also sure that the class understands, knows, or realizes what is an exothermic reaction. The internal energy, the total internal energy of the product, is actually lower than the total internal energy of the reactant, right? So what happens? What happens to this excess energy? This excess energy now flows out of the system in the form of heat, right? So this everybody understands and realizes. On the other hand, what happens in an endothermic reaction? Endothermic reaction, what happens is the internal energy of the product, total internal energy of the product, is more than that of the reactants. And consequently, what happens? So it's just the direction of Q. So this is for endothermic reaction. This is for exothermic reaction. This all of us know, right? The whole class knows this, right? Nothing new to learn. So in most cases, what happens is there is going to be a lot of when you have to handle, let me put it very bluntly, heating, cooling, etc. There are a lot of problems. We will take up some problems, example problems, where you will understand that we will take up heating, cooling, etc. And we actually started to talk towards that end in the previous class, right? So when we talked about how to calculate the heat requirement for, let's say, heating up some mass M or some flowing mass M dot, right, from temperature T1 to T2, this is what we started to discuss. And then in no time, due to some surprising reason, the discussion became quite animated, right? When I tried to tell something, class thought something, and then finally, I guess everybody got convinced. So what did I say? That when we are calculating, let's say, Q for a specific process, there are two sets of properties, two types of properties that are involved. One is the properties associated with the system and the process. So property associated with the system is how much mass you have taken, whether you want to heat 5 kg or 50 kg. Then there are something called physical parameters. So if you are going to heat up steel, whether it's 5 kg or 50 kg, your CP remains the same. On the other hand, let's say if you are going to heat up aluminum, again, it's 5 kg or 50 kg, your CP is different. This is one thing we argued. And then what is the system dependent parameter? System dependent parameter is what is the range of heating you would like to achieve. Would you like to heat up from 100 degrees centigrade to 300 degrees centigrade or 100 degrees centigrade to 500 degrees centigrade? So this, I guess, the whole class sort of understood. And then there were some questions when I said that you may not have a constant value of CP, right? You may have values of CP which can itself be a function of temperature. So you do not apply MCP delta T, but you sort of perform an integral from T1 to T2. And then there was a lot of confusion why I'm still calling CP as a physical property if it itself is a function of temperature. So the answer to that was, I think we all converged to the point that though CP is a function of temperature, but that temperature dependence brings in 2, 3, or 4 constants like this A, B, or C, whatever is written in this particular slide, what you are seeing, and those are still material dependent. So that's where the physical property of the material comes in. Up to this point, it was clear to everyone? Can I have some response? There is no response in the chat box, so I don't understand whether the class is following me. Am I audible, or I have got completely disconnected? I don't know that. Can I have some responses, please? Is it okay? Great. Right. So agreeing to this particular concept, I would now like to ask the class that in case, thanks. So I would like to, I'll place the question like this, something I'm going to ask everybody knows, so it's a very simple question. So maximum how many physical properties you might need, or we might need? Maximum, how many such physical properties we might require? See, do not forget one very important understanding. So even when you do this very simple stuff, right? Just give me a minute. So even when you do this very simple stuff like MCP delta T, need for what exactly? Coming on it. Can you look into this equation and comment what are the explicit assumptions? Yeah, video is lagging. I know that problem is happening. It's a complaint that I have placed with Microsoft Teams, with Institute administration, but then I can't do anything about it. Anik Mundul, I'm coming back to your question. Listen to what I'm asking. So when you are able to write this equation, what are the implicit assumptions? Process should be continuous. Anything else? Think in very simple terms. And also think of a situation where you come out of your comfort zone of a textbook or a question paper. What I mean to say, that you are all extremely capable of solving such problems in the framework of a question paper or a tutorial problem. What does it mean? That CP is specified, right? You are told that this particular material is heated from this temperature to this temperature and find out what is the heat requirement, and here is your CP. You take this value of CP, maximum what you might have to do, you might have to do some conversion of unit, and that's all about it. But in reality, what might happen? You might encounter a new material, or you are given some material and told you have to heat up, right? And you don't know what material it is. And that is exactly the transition what will or we have to think about from the life of a scientist, because all of you are here because you have been extremely good in your science discipline. But in engineering, don't go to the surrounding, no, Abhishek Purohit, it's not even that. It's far simpler thing. The assumptions are as follows. Number one is the material is known, and therefore CP is known, right? This is your first assumption. There might be many times, like let's say I tell you that you have to heat up steel, you go to some textbook and find out this is the CP value of steel, done. But let's say you have to heat up some barium niobate, right, which you do not know. It is not that easy to find out what is its specific heat capacity, right? So what will you say? We will go back to your boss and say, well, I do not find the data and I can't calculate. That's not an engineering approach, because you are not, when this subject was evolving, you need to understand that mass of course remains constant. Those are all taken, those are not the implicit assumptions. What I'm trying to teach you is something completely different. When you write this expression, there are two implicit assumptions. One, the material is known, therefore you know CP, right? And the second thing is within this equation is valid only if within the temperature range T1 to T2 there is no phase transition, phase transformation or phase change. That is, if you are applying it for a solid state, you are certain that the melting temperature, you are sort of given the guarantee that the melting temperature is above T2, right? If you are talking or using this formula for a liquid, then your boiling temperature is above T2, isn't it? So you are going to use this formula either for a solid or for a liquid or for even for a gas, right? But when you are using this for calculating Q, your implicit assumption number one is Cp is known and number two is there is no phase change. Am I clear to all? As I told, this is a completely different perspective what I'm going to give you, and this is a far realistic perspective. Is it clear? Great. So in that way, what are the, so there was a question somebody asked, how many physical properties at max we need? At most or at max? How many such physical properties might be necessary? And in order to give an answer to that, let me just draw a quick figure. No, Shayan Haldar, it's not as per our need. You do not need 10 properties. Of course, the specific, everything is there. So is this graph clear to all? This is an enthalpy for, yes, Ayush, Iron, absolutely, 5. At most, we might need 5 properties. 3 CPs, right? You can also transfer your phase diagram here. These are the solid, liquid, and vapor phase, and 2 latent heats. Is it clear to all? Very good, Ayush. Very good that you got this. As I told, I'm not teaching you anything new, but I'm presenting something that is known to everyone in a slightly different form. I'm asking something that is known to everyone, but I'm asking it in a slightly different form. Is this clear to all? If for a material, all these 5 properties are known to you, then you can do all the possible thermal calculations. Well, now many of you are agreeing to this number 5 and feeling quite happy that I am saying you have understood. There is again an implicit assumption. What is that? What is the implicit assumption there? When we say 5, there is an assumption. Anyone? It's just a test of how sharp you are thinking. Material is pure, Odrija? No. Material is known? No. Cp is constant for that phase? No. In fact, the pressure is constant. Very good, Shankar. Pressure is constant. Pressure is constant, and essentially we are talking about 1 atmospheric pressure. So we are talking about the normal boiling point and normal melting point. Very good. All of you who have said the other things, pure material, material is known, Cp is constant for the phase. Actually, it is not, Vivek, because by looking at the graph itself, you can comment whether you're. So let me just finish. So of course, the assumption here is pressure is constant. And then engineers are not scientists, so we are all supposed to work on the earth. Therefore, we do not worry about how the conductivity or specific heat changes in the International Space Station. And therefore, it's not only constant, in most cases, it's assumed to be. We are happy to have some estimate. I'm coming to this estimation part. It's 1 atmosphere. So that part is frozen. Now, there was a very interesting wrong answer by Vivek. And that answer says Cp is constant. Of course, the other two answers, Udrija and Shayon, these two are of course valid, but these are implicit assumptions when we were writing here. Material is known, and if it is not pure or whatever, if your material is known, you can take care of the impurity while calculating the material properties itself, Udrija. Give me some 10 minutes and I will show that to you. But can you look at the graph and comment whether Cp is constant or not? Or will there be any signature whether Cp is constant or Cp is a function of temperature? Very good, Samira. Very, very good. Excellent. Yeah. So it depends on, for a particular phase, whether you have a straight line or a curved line. If you have a straight line over the entire range, Cp is constant. If you do not have a straight line, do not worry about the slope. What is the value? I do not know. But the moment any one of the segments look like this, or whatever, Cp, what is your conclusion? Cp is a function of temperature, right? Now, if Cp is equal to constant, then what is delta H? It's simply mCp delta T. Forget about m, let's calculate for 1 kg or specific. So Cp delta T. So it has a linear dependence, and the slope is the Cp. So if you have a straight line for any of the phases, right? My scaling of the graph was not wrong, because it was completely wrong, because what will happen is in most cases delta Hv will be much higher than delta Hf. You know that for water it's 80 and 540, something like that, right? So these are completely wrong figures I have drawn, but that's enough to build the concepts. Also, the slopes might be completely different. In fact, the slope itself can tell whether, for example, you expect a much higher slope in the solid state as compared to that in the gaseous state, because we all know that the specific heat for gases is much lower, maybe. Right? So all this is clear, and everybody understands this graph. This is very easy. In fact, it is the same phase diagram. Right? So what was suppressed in this? What is missing in this data? So when you draw this phase diagram, or when you drew this phase diagram, see, today's class is actually a fun class. When you drew this phase diagram, so what was missing here? The thermal part, not only latent heat, Soham, there was no manifestation of the thermal consequences. We simply talked about at a constant pressure, temperature is increasing, decreasing, whatever. Not only Cp as well as delta Hv or lambdas. Shayon. Those of you who are writing Cp, kindly mute yourself. Kindly mute yourself. One of you are unmuted. So it's not only a question of Cp, it's all the thermal effects, all the 5 parameters we are talking about, their associated effects. That's completely missing. Another quick question on this. Can you map this graph on this phase diagram? Where do you locate this graph on the phase diagram? I won't waste time. It's simply this line, P equal to 1 atmosphere. All you are doing is this. And now looking at the enthalpy values at every temperature. All you are doing is you are looking at the enthalpy values at this temperature. Is it clear? So in fact, this line, along with the enthalpy values, gives you this plot. Is it clear to all? Okay. Is it clear to all? I guess some network issues, no response coming. Good. Thanks, Rishi, for confirming. Okay. I think I'm teaching to a reasonably senior class, that we should not talk too much about what is heat capacity and specific heat, blah, blah, blah. But still, just for the sake of completeness, because this is in your syllabus. So heat capacity of gases. I will just rush through this part. Otherwise, it will become very, very boring. So first so essentially we need to have 5 set of values. Cp. And for gases, you know that. So essentially for solid and liquid, we care only about Cp, but then for gases, we worry about these two. Because of a very simple reason, the effect of pressure on the solid phase and the liquid phase is far negligible as compared to that of gas. So we all know that. We all know what is Cp and Cv, right? So what exactly is Cp and Cv? So let me just write down quickly. So what exactly is heat capacity? It is the amount of heat required to increase the temperature. A couple of interesting things that are coming up in pedagogy wise. Increase the temperature of an object, of a body, of an object by 1 degree centigrade, by 1 degree. So we all know this. What is specific heat? Everybody knows the difference between specific gravity and density, right? Everybody knows that. And what is the unit of specific gravity? Unitless. However, what is Cp and Cv conventionally? Great, all, no unit, it's a ratio, density by density, cancels out. But then what is Cp and Cv you call? What is Cp and Cv or Cp? What is Cp? Very good. What is Cp? Sneh, just hold on. What is Cp? Shayan, there you are. Cp per kg, I have not asked for the unit. What is Cp? What is it called? So Arjav, Rastogi and Sneh Bandhu have given the correct answer actually. Or Arjav's answer is absolutely correct. It's actually specific heat capacity, but be careful about this work. We often use the terminology specific heat, and that's wrong. That's wrong. Why? Because if Cp was the specific heat, what ideally should have been specific heat? Specific heat ideally should have been, yeah, so see, I mean, Naman has written specific heat at constant pressure, and somebody has liked or made an wow or something in the chat box. Had it been specific heat, what should have been its unit? See, these are such trivial things, but there are, I mean, this is convention. You cannot say, no, I'm not going to say CP is not specific heat. We all accept to the fact that CP is specific heat. But is it actually specific heat? The moment you write it's kilocalorie per joule or kilocalorie per degree centigrade or kg per year, this, that. So is it specific heat? Specific heat for unit mass. Not only that, Samira. Yeah. No, it's not specific. It's not. It's heat capacity. Vardhan. What is specific? Then specific gravity. Just compare what is specific gravity and what is specific heat. Whatever you are writing, Cp per kg, it's energy per kg per degree centigrade, all that is fine. But is it specific? Why the word specific? Those of you, I find Arjav Rastogi is writing specific. Samira wrote, I find Sri Sai Vardhan is writing. What exactly is the meaning of the word specific? Intensive property? How? There are many properties which are intensive, which are not specific. Comparison with what? Pradipti? Others, please. I'm not going to change any concept that you know. If fixed known reference, yes, Karan, what is that known reference generally? What is that fixed known reference? I really like your answer. Like water, not like water, it is water. Specific gravity is water, right? Is the density of a material? No, not per mole. That's the molar heat capacity or the heat capacity on a mass basis. I'm coming to it. Specific heat, so Soham, yeah, specific heat would be unitless. Specific heat capacity is Cp. I would like to take your answer in total. Yes, here we use the word specific to emphasize its per unit, but that's actually a wrong pedagogy, because if you compare with other properties like specific gravity, it's a wrong pedagogy. Not that you and I can do anything, but if you compare, let's say, with specific gravity versus you talk about specific heat, specific gravity does not talk about what is the density of 1 kg of water. It doesn't talk. And I really like this answer Karan gave when he said, I just will remove only one word from your answer, Karan, that's the like water. It's no question of like, because in most cases, water being the most abundant material, right, the comparison is drawn with water. So you all know specific gravity is essentially the density of a material divided by density of water. So similarly, following the same pedagogy, specific heat would have been the ratio of heat capacity of a body. In fact, that is exactly the definition you have if you read the book. It is the ratio. There's another such funny example I'm going to give you. Ratio of heat capacity of a body to the heat capacity of an equal mass of water. This is the textbook definition of specific heat. And it is independent of any units. If you kindly look into the textbook that I have shared, this is what you will find. So here, I think not in this class, but some other class, I just told somebody I hate the word convention, but here essentially you use the word Cp. So those of you who have written specific heat at constant pressure to sort of please me, whether I was checking you know the difference between constant pressure and constant volume, I sort of give full marks to all of you, right? Because that is the convention we follow. But please scientifically understand, this is the heat capacity. This is not the specific heat. And then, as one of your friends, I think Soham, has written, maybe people use the word specific to sort of define its per unit mass or unit mole, right? So essentially it's the heat required to increase the temperature of an object, right, by 1 degree. Instead of increasing the temperature of an object, temperature of 1 unit mass of an object. So that's how it goes. So anyway, this is a sort of a, I won't say animated discussion, but this is something I wanted to highlight. So what we always refer to as specific heat, and when I ask the question, some of you are very cautious today to give an answer, it's heat capacity. But more and more you leave the shell of a scientist and become an engineer, you will realize that we always talk about Cp and Cv in your thermotext, thermodynamics text, and everywhere you will find that we essentially talk about Cp and Cv as the specific heat at constant pressure and at constant volume. So the answer that came from the well taken, that is exactly what you say, but then we realize that actually the word specific is wrong here, because specific would have mean the ratio of the heat capacity of a particular material to the ratio of heat capacity of water, right? Or essentially the heat required to heat up some material by some degree temperature divided by the heat required to heat up equal mass of water by the same change in temperature, something like that. So anyway, so heat capacity of a substance and let me also tell you, compared to what we had so far, today's class is going to be a little lower level. It's sort of very boring, very mundane stuff. Specific heat of, I mean, don't log out listening to that. But anyway, let me sort of give a statutory warning. Not too many teachers will tell that. But what I'm going to teach you is sort of simple. So the heat capacity of any quantity of substance is expressed as C right? So dQ is the heat added. These are simple stuff. I could have simply done away with it, but just for the sake of completeness, and if anyone needs a revision, I'm doing it. Achieve a temperature change delta T for an unit mass. Now what we know? We now know dQ is equal to du plus dW, right? And for a system which can only perform, there is no electrical work, this gets converted to PdV. The dW is PdV, we all know that. So from here, straight away, so dQ dt at constant volume is nothing but du dt. Because you differentiate, dV is equal to 0, so it simply turns out to be du dt, right? And therefore, Cv, in fact, I could have taught it even better, but it's fine, is dq dt, but I'm not feeling like it, at constant volume, right? And therefore, this turns out to be 1 by m. When you are talking about this cap means it's for unit mass, so this 1 by m goes away. We are essentially talking about du dt only. And what is Cp? So Cp is the whole thing. And now, what is this particular entity called? We all know it. This is actually what is called the enthalpy. So this is enthalpy, right? So I don't know why I'm rushing so much. There is a very nice discussion one can do about enthalpy. Let me just check the concept of enthalpy. So yeah, thank you very much then.